All right, welcome to Hump Day. Somebody referred to it. Apparently, well, I guess the people who are here like this paper, but I guess there wasn't a lot of votes. I think this is a cool paper. But, so today we're going to talk about Linux scalability. On Friday we will do exam review. I think I'm going to do that pretty much the same way we did midterm review. If you want, I think from last year, there's a long video of me going through compressed version of everything we covered this semester. I don't really feel interested in doing that again. I think when I did it, we also did it over 2 hours. So we don't have 2 hours on Friday. So instead, I think what we'll do is just similar to the midterm. I'll throw up one of the finals. We can go over some of the past exams. And I'll just answer any questions, right, you guys might have. Last time I checked, which was a few minutes ago, you guys were at 70% exactly. So just need one more person. I don't know if it was greater than or equal to, but whatever, right? I mean, I'll probably give you that one, but unfortunately, I haven't written any short answer questions yet. So, but as soon as I do, you know, but now that I know I'm going to have to release one, I'll make it really easy, right? No, that's okay. We've been outlining the exam, so we have some ideas. But please fill out the course feedback form. I'm happy that 70% of the people have filled it out. If you're in the 30% of people who haven't, please do it. It's very helpful for us to find out what you guys think of the class and ideas about how we can improve for next year. Assignment 4, yeah. So there is an assignment 4. The next week, assignment 3 is due. The exam is on Monday. So the exam, I think our slot is from 3:30 to 6:30. The exam is 100 points. It's roughly, I consider it to be roughly twice as long as the midterm. The midterm was 50 minutes. The exam we have 3 hours for. So you should have plenty of time to complete the exam. People in the past have not needed the entire 3-hour period. It'll also mean that we'll probably spend 10 minutes just letting the TAs prep the room at the beginning of the exam. But don't freak out. You guys have plenty of time. Again, it's a 100-point exam in 180 minutes. So you guys should have plenty of time to do it. The procedures will be the same as the midterm. The only difference, I think, will be, and we will do the same thing, we'll post the seating chart on Monday at some point. It'll also be posted on the doors. Your exam will be at your seat. It'll have your name on it. If there's any lingering left-hand desk requests that still haven't been filled, if you asked for one for the midterm, you'll get one again. If you didn't, and your handedness has changed, or you just didn't like, you know, I was watching it. It's like the one time it's good to be left-handed is with these visualizers, right? Like, it's pretty awesome. He's just like, wow. I was thinking maybe he taught himself to write left-handed just so he could teach this class. Anyway, so if you need a left-handed desk, ask us. Otherwise, you know, again, the exam will be on Monday. Throughout the rest of the week, we're going to try to do some augmented office hours. We have a big stretch planned for Thursday night. I'm hoping, I need to ask permission for my wife to be here late, but I'd like to be here for the assignment 3 turn-in, so we'll have pizza. We'll do sort of something similar to what we did last time. And then you'll be done. So any questions about administrivia? I think I covered everything I wanted to cover. And again, as soon as you guys pass these thresholds for the exam questions, whichever comes first, you pass the threshold or I have a question to release, right? The question, I will post the questions on Piazza. I'm not going to use any other mechanism for distributing it I think the people in this room are not a problem, but if you're within the sound of my voice and for some reason you're not on the Piazza forums, that's where you will find out. If you show up at the exam and you're like, oh, you released exam questions? That happened last year? It's kind of sad. But anyway, so please monitor the forum because that's where the questions will be. Any questions? All right, so let's talk about analyzing Linux scalability or an analysis of Linux scalability to many cores, right? So this paper is a couple of years old, but I am quite fond of this paper. I like a lot of things about it. If you read it, it has a certain tone to it that I appreciate. For example, I'm trying to remember right here, right? I mean, it is common when writing papers to try to claim that you have made a large contribution, right? Instead, this paper says that this question is difficult to answer conclusively, but we attempt to shed a small amount of light on it, right? So this is a nice sort of restrained approach. It's also what I think, so I'll put this in context in a minute, but I think this is a great example of just applying standard good software engineering and good performance analysis to a problem rather than overreacting and redesigning the entire system, right? So what is this paper? I mean, we talked a little bit about, we've talked all semester about how operating systems have evolved in response to technology trends, right? We also talked at one point, not in a huge amount of depth, about some new kernel designs. So where does this paper fit in? What is this paper responding to? Again, this was, I think, 2013, maybe 2012. So a couple years ago. But what technology trends is this paper responding to? And what sort of trends in operating system design is it responding to? The technology trend should be easy, yeah.
The trend towards multi-core systems?
Yeah, sort of. And this isn't I don't think you would describe a 48-core machine as massively multi-core, but it's a multi-core machine, right? And it's got more than 2, right? And it's got more than 4 and 8, right? And so it, in a larger number of cores per machine is the technology trend. What's the system design trend that this is responding to? Yeah, Kevin.
Being able to take advantage of that with teaching simultaneity. That's what the
Yeah, well, so what if, so this paper is kind of a, if you read a bit of the introduction, they're kind of saying, look, other people have proposed X, right? In response to this trend towards multi-cores, we're not sure that we need to do X. What is X? Yeah.
Severely redesign the kernel of Linux.
Yeah, like start over. Not even Linux, right? Just completely redesign the system from the ground up. So in the introduction, they talk about several previous systems, one of which we've alluded to in this class but never really discussed in detail, called the multi-kernel, that was work from a couple years back. There's also work by these very same authors addressing this, right? The Cori operating system is something that Silas Boyd Wissaker also worked on, right? So it's kind of cool. I mean, these guys are sort of playing both sides of it. They're saying, on one hand, hey, let's explore these new cool designs. On the other hand, is it really that hard to get Linux to scale to 48 cores, right? So what they're arguing for here is they're saying, look, rather than going out and starting over, right? And look, I mean, when Linux and these other operating systems that you guys use today were designed, you certainly didn't have 64-way, 128-way cache coherent microprocessors to run them on, right? So you can argue, I think, and you could argue quite well, that an increase in the core count might actually cause the need for a fundamental redesign of the operating system. What's one way to argue against that, other than to do what they did, right? Which is to show, hey, we can fix these problems. If someone was saying, hey, there's this brand new technology trend and we immediately need to just ditch Linux entirely and Windows and Mac and just completely start over from scratch. Gino.
Well, I guess there's 2 things. The first thing is there's going to be a brand new trend the next day that you're going to have to redesign your whole system for again.
Right.
The next thing is that trend might not last or even be feasible for long enough short period of time.
Okay, well, let's say these are real trends, right? And let's say that it's a real fundamental shift. Kevin. Okay, but again, I'm saying this is required, right? There is no way, there's no evidence that these existing systems are going to be able to cope with this new hardware feature, except for the fact that what? That these designs are 40 years old, right? I mean, there's been a couple of other technology changes along the way in the last 40 years that have caused these operating systems to already adapt, right? So they're not to say that this is, Linux and these other systems offer the be-all, end-all approach to how we're going to design operating systems forever and ever, amen. But, you got to have a pretty strong argument to argue for starting, right? These are pretty resilient systems. So in order to make this case, what did the authors of this paper do? Their argument is, their hypothesis is, Linux can scale to large numbers of cores. What do they do to try to argue for their hypothesis? Or just explore, let's say that this is science rather than the computer scientific method, right? and we're actually trying to evaluate this hypothesis, what would you do? What's the first thing that you would do? My hypothesis is Linux will scale to 48 cores, right? The first thing I'll do is what? Test it. Does it scale, right? Is there a problem? If there's no problem, then go to done, right? That's not hard, right? Let's assume there is a problem, right? Which is probably maybe why I formulated this hypothesis in the first place. Then what do I do? Yeah.
Make some changes to try and improve.
Yeah, fix things, right? Which is what I really like about this paper. I mean, this is not magic, right? There's no fancy new design. It's just like we ran tests, we identified bottlenecks, we fixed the bottlenecks, then we repeated the tests, then we fixed more bottlenecks, right? And there's nothing, I mean, some of the techniques that they apply are kind of clever, right? There's one sort of cool new idea in this paper, but a lot of it is just standard good software engineering, standard sort of performance improvement based on benchmarks and evaluation, right? So that's one big contribution in the paper, is that they make these changes. So there's two more, right, that I would say. There's a new technique and there's a new tool, maybe. So first of all, what are they focusing on here? They're focusing on scalability, but scalability of what? And scalability of not what? Yeah.
They chose good benchmarks that look at standard uses of the system.
Right, but it's not just uses of, okay, so when you say the system, right, so this is very important, right? Let's say I run this app, and it runs fine on 1 or 2 cores, and then I run it on a large core machine, and it's not very much faster, right? Therefore, the operating system does not scale to large numbers of cores. True or false? Why? Could be my benchmark, right? What if my app doesn't scale very well? So what they've done is they put together a benchmark suite that is designed to test kernel scalability, right? They're putting together benchmarks that are either sort of, they scale nicely already, or are kernel intensive, right? So what they're trying to do is make sure that they're stressing the kernel, right? Because application scaling problems are their own. That's an own set. That's an own. Application scaling problems are their own problem, right? What we're trying to focus on here is does the kernel start to become the bottleneck, right? And then what's the third contribution? There's one final little, to the degree that there's something new and novel in this paper, other than just good, high-quality performance analysis and software engineering, which is, sadly more novel than you would like. What's a new idea that they introduced here? Yeah.
Sloppy counters.
Yeah. So this idea of what are called sloppy counters, right? It's a great name, by the way. If you invent something new in an operating system, you have to have a cool name, right? They could have called them like approximate counters, right? Just kind of what they are. But sloppy counters just sounds a lot more interesting, right? So 3 contributions, right? One is that we fixed bottlenecks in the Linux kernel, right? The second is we have a new technique that eliminates one potential source of bottlenecks by applying a sort of new tool to address them. And the third contribution is the benchmark suite itself, right? All right, so let's talk first about, right? So, and then the other thing in the introduction that's kind of fun, where do you see, there's a number of different places where Amdahl's law is applied here, right? Where do you see Amdahl's law applied quite well? I mean, give me some examples of Amdahl's law being applied throughout this paper. Amdahl's law and its corollaries. When they talk about bottlenecks, right, they say, we identify a bottleneck and then we fix it, right? But then they say something else. What do they do next? What does identifying one bottleneck frequently do? Yeah. Well, it doesn't cause more bottlenecks. You hope it doesn't cause more bottlenecks. It could, right? If it does, maybe you haven't fixed anything, right? But frequently what happens is that it exposes another bottleneck, right? So remember, Amdahl's law, if I have this one big part of the system that's making this huge contribution to performance, let's say I reduce it down and the performance is now improved, there's some other problem, right? Now, the problem has been there, right? But its impact on the relative performance of your app has been hidden by the first thing that you fixed, right? So as soon as you fix a bottleneck, you have to go back, rerun your performance analysis, and determine what to do next, right? Okay, so let's talk a little bit about what it means to scale, right? To scale to multiple cores. Let me pull up. Oh, there's a lot of work on. We'll go back to this, but let's look at, let's look at this. Sloppy counters, where's the graph I want? There it is, okay. So what does it mean for an app to scale? What ideally would I like? What would I consider to be perfect scaling for an app? Yeah?
The performance multiplies with number of people.
Right, if I get X performance using one core, then what I want with 48 cores is 48X, right? That is the golden ideal, right? That's what I want. Here, for some of the benchmarks, I wonder if I can zoom in a little bit. I mean, this, we can look through some of the more detailed results, but this is one of those cases where this graph essentially, oh, come on. Why won't you let me do that? Well, anyway, you can kind of see it. This graph is pretty much the entire paper, right? It is, right? I know it's just a lumpy little bar graph, right? And if you read Edward Tufte's stuff, right? He probably would. Oh wait. Oh God. And I thought you guys thought I was funny. No. Really? Oh, this is terrible now. Oh wait, there we go. Sweet.
Much better.
Let's see. Why is it rotate view counterclockwise? There we go. Phew. Okay. Yes, I'm so much better with my own stuff. All right. So there's the entire paper again. Not the. So what we want, right? So essentially, this is the relative per core performance of a subset of the various applications that they ran, right? And what this does is it compares the stock Linux kernel, right, which are the white bars. I have all sorts of issues today, with the changes that they made, right, the patched kernel, right. And what you can see is that for certain benchmarks, like Apache, right, I mean, Apache is terrible. So if I ran, so essentially, let's say I'm a web administrator, right. I've got Apache, and my website's getting slow, right? Because it's your personal website, and you're getting popular, right? People are, so I'm like, I need more. Clearly, I've got a 2-core machine. Clearly, an 8-core machine is going to solve my problem, right? But why stop at 8? I might as well get a 48-core machine, right? While I'm at it, and here's the relative performance I get, right? It's not even clear that Apache has improved much at all from all those extra cores you added, right? Your wallet has gotten a lot lighter, right? But Apache hasn't gotten any faster, right? So that's quite slow, right? Performance of other things that you would want to scale, like Postgres, right? Postgres is a database server. Database servers to some degree a database server and a web server are both applications that we've talked about in the past as naturally, they should be easy to parallelize, right? They're sort of examples, particularly web servers, right? Examples of what you might call an embarrassingly parallelizable workload, right? I mean, every request that Apache processes is essentially its own little piece of work, right? I should just be able to farm those out to a bunch of different Apache processes running on different cores and get great performance, and I'm not, right? And the performance bottleneck here, it turns out, is Linux, right? Which is pretty interesting, right? I mean, imagine how frustrating it is to be an Apache developer, right? You put all this time and effort into running this thing, improving, the isolation between the processes that are required. And of course, your job's not that hard because it's serving websites, which is, again, kind of an easy thing to parallelize. And you're not getting great performance because Linux's shared data structures are killing your performance, right? All right, but you can see that, there's this, really, really significant performance improvement that they were able to achieve for a bunch of different apps, right, where we were struggling, right? Anyone know what Exim is? You guys got to get some machines to administer. Yeah, it's a mail server. Memcached. Anybody know Memcached? It's a very simple little key value store that runs in memory. It's very fast. Yeah.
Did they talk about, or do you know how the trend goes between 1 and 48 cores?
Yeah, we'll look at that. Right. Yeah. So let's look at an example of this, and then we'll sort of work backwards to figure out what's causing this. Right. So here is an example. Let's look at Apache, because Apache was kind of bad. There we go. Right. So. And this is actually pretty awesome. So again, I'm going to try to zoom in, and hopefully I won't flip the whole page around. Oh, sweet. Thank you. Now you're responding to me. All right. So here is Apache. What this axis is showing is the throughput, but this is scaled per core. So this is throughput per second per core. Right? What would I want this graph to look like? Right? No, that would be awesome, right? But that's not possible, right? This is throughput per second per core, right? Ideally, what would this look like? Straight, right? I'd add a core, I get a set amount of throughput. Again, if it went like this, I want that system, right? That's pretty awesome. There's something very special about Core 32. Core 32 has added way more performance than Core 31. Yeah. No, with homogeneous cores, not so much. But yeah, so what I want here is I want this to be flat, right? And here's the stock performance. I have no idea what happens in between 4 and 12 cores here, but that's interesting, right? So the stock performance is pretty bad, right? And what this is showing is as I add cores, each additional core is getting me less and less performance, right? In contrast, right, when I look at the patched kernel that they ran, right, closer to flat, right? Definitely much better. Definitely something that might encourage you to buy a 48-core machine if you were using Apache, right? Other than not this, right? And the other thing that's cool here too is that if you look at the user and system time, right? Now this is over here. So this, right? So this is CPU time per request, right? What do I want that to look like? Also flat, right? But this one, it's bad if it's going up, right? If it's going up, it means that as there are more cores, something is creating overhead that's causing each individual request to get slower, right? Here you can see that this is what's causing this, right? So the reason why I'm getting a little bit less throughput is because the system time, right? The kernel time per request is going up slightly, right? What's really cool to see here, right, is that the user time, right? So this is Apache's time per request is flat, right? Like Apache is doing a very nice job. I don't know what these look like for the unpatched kernel, right? But Apache is clearly doing a very nice job of scaling properly, right? And the bottleneck here is Linux. All right, so let's talk about some of the problems. So what is the enemy? Oh Christ, it's going to do something weird again. What's the enemy of scalability? Right. So if I have a bunch of cores, talk about some of the other things in a minute. They have a bunch of reasons why, or 5, I think, 5 reasons why, as I add cores, performance might not improve. Right? So what's one that should be pretty obvious?
Shared data structures.
Okay, maybe. There we go. Yeah. So remember, locks and shared data structures, not necessarily the same thing. I can have a shared data structure without a lock, right? And I can lock things that aren't necessarily shared data structures. So a lock, right? So imagine, right? Again, so when I have, one way of thinking about this is when I have perfect scalability, tasks that proceed on all 48 cores can essentially just proceed completely in parallel, right? They talk about if there is no, so you can probably prove this on some level, if there's no communication between the cores that's required, then there should be no overhead to scale, right? What is that kind of equivalent to, though? If there's no communication between the cores, what would be another way to achieve the same type of scaling without buying 47 more cores, yeah.
Having 48 single computers.
Yeah, just like 47 more machines. And what's better, I can put them anywhere I want, right? Because they don't have to communicate with each other, right? To some degree, if you've looked at things like MapReduce, this is kind of what you do, right? Because if you can break your computing job into pieces that have no communication between them, then it doesn't matter where they run, right? And I can distribute things to my heart's content, right? Now, the fact that I'm running on a shared memory, machine probably means that that's not exactly what I want to accomplish, right? But that is sort of the ideal thing. To the degree that I lose that perfect scaling, right? What does it really boil down to, right? There's something, well, I mean, with a lock, let's talk about locks, right? So why does a lock break that assumption that everything can proceed in parallel? What does a lock effectively do to a bunch of parallel tasks? So let's say I have a task that I'm going to run on a bunch of different cores, and that task grabs a lock, right? What is the lock? So everything's running in parallel until it's fine, and then I hit the lock. What does the lock do to those tasks? Yeah,
Forces them to run in serial.
it serializes the entire bunch, right? So, so again, I mean, you can think about it. If they're running in parallel, I really have no idea how much progress they've made, right? And that's kind of a race. It's like they're all on separate lanes of the freeway, right? Once I have a lock, it's like reducing the freeway down to one lane, right? And you guys know what happens, right? And this is not most of you have probably not driven on a 48-lane freeway, right? That's going down to one lane, right? Unless if you've lived in Seattle, in which case getting on the bridge is like that, right? But most places, but imagine, I mean, you have a 4-lane freeway, it goes down to one lane, that's a huge bottleneck, right? So the lock is forcing those tasks to run in serial for as long as they need the lock, right? So what's one obvious way to improve? Let's say I have to use a lock for some reason, right? What's one obvious way to improve scalability? So it's not just that I need a lock. There's something else that's involved. Gina?
Instead of just having to wait for the lock to be free, have it do something else that's useful.
Okay, I could do that, maybe, but I'm still going to eventually have some lock contention. But lock contention is also a function of what? Yeah, Doug.
Like reduce the critical section or increase the sort of number of ways to kind of access that critical section?
Reduce the critical section, right? I mean, that's really the big thing. If I have a task that only needs a lock for 0.1% of the time, then again, it's like a freeway where there's only a tiny little place where you have to bring. Well, now again, it's a bad example because people, when they see that, they slow down and everything. But imagine like people were these like perfect ideal drivers that always drove the fastest speed possible. Well, anyway, it's not a good metaphor. Sorry, it was one of those. It was a trap, right? Like it seemed like a good metaphor, but then as you got inside of it, you're like, oh, that doesn't make any sense. Anyway, so locking shared data structures, right? That's one big source of reduced scalability, and one of the ways to address that is simply reduce lock granularity, right? Or in another case, when we look at these sloppy counters, find a way to do things in a way that's a little bit more approximate that preserves the same properties that you were using a lock to achieve, right? We'll talk about those in a minute. Okay, so another source of slowdown, remember, so these are, and this is another difference with the 48 separate machines, right? So a 48-core machine, we're talking about a 48-core cache coherent computer, right? If you guys have taken architecture courses, what does that mean? Right? What does it mean to provide cache coherence for multiple cores? What's a cache? What are we talking about when we talk about cache coherence in this case? Nobody knows? Oh gosh. You guys cannot graduate. You're not ready. Don't know what a cache is. Yeah.
All cores are going to have will see the same information, and even though the caches might be split.
Right, so again, I mean, when you bought your machine, there were probably all these specs, right? Like, ooh, it's fast because of this and this and this, right? What were some of the things that makers brag about when they brag about how fast their machines are, right? Yeah.
Level 3 cache.
Yeah, well, level 3. I mean, if you're lucky enough to have a level 3 cache, right? level 2 caches, level 1 caches, right? So again, I mean, the universe of storage is much more complex than just registers, which are lightning fast, right? And memory, which is relatively slow. You know, we've thrown a lot of different caches at things, right? And depending on the organization of the machine, most of the time cores will have exclusive L1 caches, right? The L1 cache is the closest cache to the processor. It's the fastest to access, right? Slower than an L1 is a L2, right? Sometimes cores will have their own L2 cache. Sometimes those L2 caches will actually be shared with multiple cores, but not the same number as the entire machine, right? So I might have 48 cores where they each have an exclusive L1 cache, and then each pair share an L2 cache, right? So this can get arbitrarily complicated, right? What about caches makes it difficult to produce a coherent view of memory? And coherence is exactly what he said. It means that any read from a memory address should return the latest value, right? The latest value, yeah.
If core 1 writes something, core 2 writes core should be able, has to be able to see it in that cache, or else they'll have different.
Right, so cache coherence is, here's the simplest version of cache coherence. 2 cores, L1 caches, right? Core 1 reads from a byte of memory. What happens is that byte of memory gets loaded into the L1 cache in order to accelerate future accesses to that memory, right? Everything's fine until processor 2 reads from the same address, right? So processor 2 now loads the entry into its cache. Now as long as we're reading, everything's fine. What causes the problem? Writes. So when processor 1 writes to its L1 writes to a value that's stored in its L1 cache, what does the cache coherence protocol have to do? Yeah. Yeah, I've got to go to every other cache, and I've got to figure out, first of all, is the value in there? And second of all, if so, I need to update it, or at least invalidate it, so the next time the processor reads that address, it actually has to go all the way to memory again, or has to fetch a new value, right? Now, you know, you guys have just gotten through, you know, as some of you guys were sitting here for 396 talking about scalability, right? How badly does that algorithm scale, right? When I have lots of complicated memory addresses. Does it get, you know, imagine, so this is hard enough if I have like 4 cores, right? We're talking about a 48 core machine, right? Yeah, Kevin. It scales badly, right? So cache coherence, and this is one of the reasons why people have, when people, you know, talk about these massive machines with like thousands of cores, we are no longer talking about cache coherent systems, right? Those machines, despite the fact that they might share things like memory, have different, they provide different expectations to the cores, right? Not every core is guaranteed to see the latest address, and so you have to do things differently, right? Usually those machines provide some cache coherent memory that can be used by groups of cores, but once you get to thousands of cores and you look at these massive supercomputers, they don't do that, right? Because providing cache coherence gets so expensive, right? So what's another scalability bottleneck, right, on a 48 core machine? So we just talked about locks, right? And locks are kind of like, oh, okay, well, you know, at least with a lock, I can see that I've got the lock and I can fix it and reduce the lock granularity. But now I've got something even worse, right? Yeah. No, we're not. We're still talking about shared memory here. Yeah, Paul. Yeah. No. I just led you there. What have we been talking about for the last 5? No, this is not a change of subject. Yeah, but. Yeah, the cache coherence protocol is now getting in your way, right? So if I have a bunch of cores that are all reading and writing from the same memory address, right? It doesn't even matter if they're using a lock, right? This is why it's terrible. With a lock, at least you think, I can get rid of the lock maybe or do something more clever. With the cache coherence protocol, you're not even using the lock, right? You're just reading and writing to the same byte of memory. And if you looked at the paper, it's actually worse than this. Does anyone who knows something more about caches want to tell me why it's even, what is false sharing? Some of you guys that have taken hardware class. Anybody know this? Anyone know what cache lines are? Oh, I'm serious, man. Okay, so caches don't cache bytes of memory, right? What caches do is they cache lines, right? Lines are chunks of memory. They're not huge. They might be like 64 bytes of memory, 128 bytes of memory, right? But they don't, the objects that are in my cache are not individual bytes of memory, right? If they're individual bytes of memory, the cache coherence protocols would get even worse because I'd have to be tracking things at a byte level. So I don't do that, right? And the other reason, so what's the other reason that a cache might want to load a whole line, like 32 bytes or 64 bytes, into the cache when only one byte of it is accessed? And it's a one-word answer to this, something we talked about earlier this semester. Locality, right? I mean, you've got a little struct. That struct is 16 bytes, right? You accessed one byte of it, I bet you're going to access another byte, right? So I pull the whole struct and the line of memory that it sits on into the cache. How does that make the cache this cache performance bottleneck worse, though? Yeah, Kevin. Yeah, so this is what they call. Oh man, I kind of need to do this example, right? So this is what's called false sharing, right? And I'm going to use chalk. It's pretty scary, right? So imagine I have 2 bytes of memory. It's pretty easy, right? Just rectangles. So this byte is foo, right? This byte is bar, okay? And actually, there could be other bars here, right? Let's say that bar is being frequently read from by multiple different cores in parallel, right? Now, go back to your cache coherence protocol. Does that create problems? No, why not? Because the reads, right? So we're good, right? Except for, what if foo, now foo could be completely unrelated, right? Foo has nothing to do with bar. They just happen to end up close to each other in memory. Sadness, right? Because foo, there's one core that's just writing to foo periodically. Like foo's got a counter in it, right? So the one core keeps writing to foo, okay? How did this just get really bad?
All the caches have to get updated on every write to foo.
Because foo and bar are on the same cache line, right? And so the cache coherence protocol doesn't know that foo and bar aren't related to each other. Remember, it doesn't track accesses within the cache line. All it knows is that this cache line is loaded on 48 cores, and every time somebody writes, I've got to go around and run the cache coherence protocol and figure out everybody who's got it and invalidate their entries or update, right? So this is what's called false sharing, right? The reason it's called false sharing is because foo and bar actually have nothing to do with each other, right? There's actually no need to update bar when someone writes to foo, right? How do I solve this problem? What's the simplest solution to this problem? Yeah. What's that? Well, I'm going to cache. No, I want to cache both foo and bar, right? I want bar in my cache, right? I don't know why I'm reading from bar so often, but I am because it's cool. But what do I do with foo? Yeah. Put them in different cache lines, right? If I can get these things on different cache lines, then I'm fine, right? But in general, this doesn't always happen, right? So one of the other things that they do in this paper is they go through and they find cases where there's false sharing happening, and they reconfigure things so that those 2 values no longer end up on the same cache line. Yeah.
Is that something where you change? Is that something like on the application level where you change the layout of your memory? Or is that something
Yeah, My suspicion is that Linux already has some flags and things for doing things like this. But really, yeah, I mean, the problem is you really have to get the compiler to lay out things differently, right? You could put some padding on foo. I mean, again, cache lines aren't necessarily all that big, right? So one thing to do would just be to pad foo up to a cache line size, right? And then you don't have to worry about it because it's on its own cache line. If you had a variable that was very, very frequently accessed, it might make sense for it just to occupy its own cache line, even though you're going to sacrifice, I don't know, 127 bytes of memory or something like that. Who cares, right? It's better than having to wait for the cache coherence protocol to run constantly, right? So that's another thing that they did. All right. let's see. Right, so there were a couple of other, what are a couple of other bottlenecks, right, that they address, right? What's a few more reasons. So up till now, what we've really been talking about is just getting the cores themselves to be able to operate independently and reduce the contention between cores when running big, when trying to scale workloads to multiple cores, right? But what else can happen? Yeah, Doug.
I/O bottlenecks?
Yeah, what if, well, I/O, right? So what do they do in this paper to work around I/O bottlenecks? Anybody read the paper? Yeah, Natasha.
Didn't they use some sort of file instead that stayed in memory? They weren't
Yeah.
addressed.
Yeah, they use RAMFS, right? So Linux has support for allowing you to mount a file system in RAM, right? The pros, it's super fast. The cons, it's gone when you reboot, right? But they don't care. They're just running these as benchmarks. Yeah, so they moved all the files required by these benchmarks into a file system that was running in RAM, right? So they essentially eliminate all the I/O bottlenecks, right? But okay, but maybe it's not an I/O bottleneck. What else could be bottlenecking the system? Yeah. Yeah, I don't know. Are these now? I don't remember if they ran these using I guess, yeah, no, they did, right? So they ran these using networks, so they addressed some networking bottlenecks. But really the answer is anything, right? I get the cores out of the way. I could be saturating the memory bus, right? I could have problems in the networking driver, several of which they fixed, right? So, so it's possible that the problems that aren't all core related, right? All right, so let me quickly talk about sloppy counters and then we'll be done, right? So who can try to explain so-called sloppy counters? Who wants to give it a go? It's a cool idea. So first of all, what are sloppy counters? You guys have probably, hopefully, for assignment 2, implemented something that sloppy counters are designed to help do. What's a frequent primitive within kernels that I use to track the use of kernel objects? Yeah. Negative. Sloppy counters, right? What have you guys probably used in your OS 161 kernel? Yeah. Yeah, it's on process IDs. Particularly when I have potentially shared data structures, right? That could be accessed by multiple.
Semaphores?
No, we already got that one.
Oh,
yeah. No. This is an approach to being able to track when things are used and when they're ready to be destroyed. Yeah. Reference counts, right? So reference counts are a great way of being able to track who's using what on your system and figure out when certain things can be safely deleted, right? And essentially, reference counts are very similar to the idea of garbage collection in Java. I keep a count of number of references to the object. When that count falls to 0, the object is safe to remove. Until then, someone's got a pointer to it, right? So I can't get rid of it, okay? So how would reference counts potentially cause a bottleneck on a multi-core system? A couple of ways, yeah.
Modify reference count has to be locked.
Yeah, so I need to grab a lock to modify the reference count, right? This is kind of unfortunate, right? Now I'm back to my worst case scalability problem where I'm not even talking about weird memory cache coherence stuff, right? You just had to get a lock, right? That stinks. So what do they, you understand how sloppy counters work? How do they do this?
So
James?
basically, each CPU gets its own, well, each CPU just grabs a number of references to start with, and then certain ready, then it just gives it from the CPU rather than the total.
Yeah, so essentially what I do is it's like I grab some spare, so you can imagine, like, you can almost imagine a version of this where you would trying to coordinate with some friends, right? So essentially what every core does is it just grabs a couple of spare, whatever they are, references to some object, okay? Then when threads running on that core need a reference, it's possible that the core already has a spare one lying around that just hands out, right? And then when the thread's done, it hands it back, okay? So it should be pretty easy to see how, in that case, I can satisfy a lot of requests without, without accessing the shared data structure. How do I keep this safe, right? So reference counts are designed to do one thing, right? What are reference counts designed to prevent from happening? It's a safety feature. Yeah. Yeah, I don't want to get rid of it too early, right? I don't want to garbage collect or delete a shared data structure while people are still trying to use it, right? So given the way that sloppy counters work, and you can look at a more detailed description in the paper, what are they most appropriate for? What effect is it going to have that all the cores are sort of grabbing a few spare references? Yeah?
It's never really going to be deleted, so you need to use them for structures that are very infrequently gotten rid of.
Yeah, so it's not that they're never going to be deleted, right? Because their sloppy counter implementation allows the kernel to collect the sloppy counters from all the individual cores, merge them back together, and delete the object if needed, right? But that's now an expensive operation, right? Because I have to get the sloppy core from every counter, right? Sloppy counter from every core, right? But for certain types of entries that are not removed very often and are very frequently accessed, sloppy counters are a nice fit, right? Because it allows me to preserve the correctness property that I wanted, right? While eliminating a lot of the bottleneck of access in the lock, right? Does anyone remember where they use sloppy counters? There's a couple of places where they apply this technique. One is that Linux maintains a cache. This is useful. Maybe a little bit of exam stuff here. A cache mapping directory path names to inodes, right? So in theory, that cache is located on disk, right? The disk is the authority. The file system stores that information on disk, but in order to make the process of translating directories faster, Linux maintains a cache, right? So when you're translating a path name and you ask, what does user point to, this path name component, Linux can actually answer the question from the cache, right? Those cache entries, while they're being used because there's some operations on them, have reference counts, right? But for some common, so what would be an example of a path name component that you would expect to be in the directory translation cache most of the time? Yeah? No, why not? Why wouldn't root be in there? Because it's constant, it's 2, right? I don't need to cache root, I can define root, right? But what else would be in there? You're getting warmer, right? Just work. What's that? Yeah, everything in like the top level, user, lib, var, like stuff, the base name of paths on the system that get accessed frequently, right? So, and this particular subsystem, because of the pattern, so some of these benchmarks also frequently translate paths in the same directory, so they're frequently hitting this cache. And this cache was one place where they applied sloppy counters to improve performance. All right. OK, so on Friday, we will do exam review. And then on Monday, we'll have an exam. Good luck on assignment 3. And check the calendar for updated office hours for the next few days and next week.